the losses in the transformer, right? As we know, this is an electrical device, so it may have some resistance, some magnetic field, so it may have some losses that will happen into the transformer, right? And we know the efficiency we calculate for each and every machine or the equipment. By calculating the efficiency, we come to know how the performance of that particular machine is better or not. So we just get it by the efficiency. But before learning the efficiency, before calculating the efficiency, we should know first the losses in that device. So let us take first the losses in the transformer. Now, in transformer, there are mainly two losses. One is called the iron losses and second is called the copper losses. Iron losses and the copper losses. Let us see one by one what is iron losses and what is copper losses. So this is a theoretical part. You'll come to know by just reading this sentence. So iron losses are caused by the alternating flux in the core. See, we are giving alternating current to the transformer winding. So transformer winding will produce the alternating flux, and due to that there will be a magnetic losses taking place into the iron core, and these are called the iron losses, also known as core losses. As these are happening in the core, transformer core, so these are also called core loss, iron loss or core loss, same thing, don't confuse. Iron loss is further divided in two types, two groups, hysteresis loss and the eddy current loss. Now again let us see in detail what is hysteresis loss and the eddy current loss. You know this curve, this is the hysteresis loop. Maiti ka ha curve? This is called the hysteresis loop. The curve which is drawn against intensity and the flux density. So this curve is drawn, which is called the hysteresis loop, or sometimes it is called BH curve. On the x-axis there is magnetic field intensity. On the y-axis there is flux density. The core of the transformer is subjected to an alternating magnetizing force, and for each cycle of this EMF, a hysteresis loop is traced out. So the power is dissipated in the form of heat known as the hysteresis loss, and is given by this equation. Now you can just remember this equation, there is no derivation for it. The loss which is given by the hysteresis loop, which is known as the hysteresis loss, and particularly the loss which is in terms of the heat. The iron core will get heated, and this is due to the hysteresis loss. Right? So what does this curve means? See, if you know this curve, what it have, the intensity and the flux density. How this curve is plotted? Suppose this is the 0 point. Initially, no magnetizing effect is there. So we just give the supply. So there will be a production of magnetic field. So as the magnetic field intensity increases, magnetic flux density also increases. So this is gradually increasing and up to this point. For example, this is point A. Now we are decreasing magnetic field intensity, but the flux density will not come to 0. This is called, there will be some residual magnetism present in the core. So this part, which is what the magnetic flux density, still present as we have reduced the intensity. So to make this magnetic flux density 0 at this point, we need to apply the magnetic field in opposite direction. So we'll change the supply. So at some interval, the magnetic flux density will comes to 0, but at that time we have supplied negative intensity. And this is continuous, the loop will be continuous, magnetic flux density will be negative now. Again at this point, say point B, the magnetic field, we have stopped increasing the intensity. Again we are decreasing the intensity, then the flux density also decreases, but at intensity becomes zero, flux density not becomes zero. This is what the residual magnetism always present into that core, into that magnetic material. And why it is a loss? The area under this core is known as the loss, which is called the hysteresis loss, or we can say it is a magnetic loss, right? So magnetic field, as one point in the electromagnetism we have seen that we can produce the magnetic field, but we cannot control it completely, right? So this is what the reason there is a residual magnetic field and we cannot complete it fully, right? And when we draw the graph of the intensity versus density, we can have the hysteresis loop. So area under this loop is known as the hysteresis loss, and which standard formula is given by this pH, which is equal to Kn B raised to 1.6 maximum, which is maximum flux density, frequency into voltage. Now where Kn, which is a proportionality constant, which depends on the volume and the quality of the material of the core, which is used in the transformer. F is the supply frequency that we already know, and Bm is the maximum or peak value of flux density. Only this proportionality constant you need to keep. So this equation you just keep in mind. Maybe the MCQ's point of view, this may ask hysteresis loss. So hope you understood. Then next one is the eddy current loss. Now we know that the core is made from some conducting material. What we have, silicon steel. So it is made from the steel, and we know the steel is conducting material. And we are giving supply to the winding. The winding is wounded on the core. As the winding is wounded on the core, we are giving supply to it. It produces strong magnetic field which is circulating around the core. And as the core is also made from some metal, some conducting material, so EMF will get induced in that core. And that EMF will circulate a current. This current is known as eddy current. Remember, this current is circulating in the core, in the iron core, not in the winding. And as we are not using this current for doing some useful work, so this will be treated as a eddy current loss. Right? Means what? The core itself will cut the fluxes and EMF will get induced in the core, which is made from the steel. Steel is a conductor, right? So it will circulate a current, and that circulating current is known as eddy current loss. As we are not using it, it is unuseful, so it is a loss. So this eddy current loss can be minimized by making the core with thin lamination. As I told you, at the time of losses, we'll tell you why laminations are provided for making the core. So this is what the reason. We need to reduce the eddy current loss. What is eddy current loss? The circulating current in the core, which is a eddy current loss. And we need to reduce it. So by making the laminations of that core, we can minimize the eddy current loss. So there will be opposition to the magnetic field, simply. The equation of the eddy current loss is given by PE. It is denoted by PE, right? So, which is equal to KE Bm square T square F square V. Again, you need to remember this formula. There is no derivation. Directly remember this formula. Where Ke is the coefficient of eddy current, its value depends upon the nature of magnetic material. Bm is the maximum value of flux density, as you know. T, see, this is small t, not the capital T, which is the thickness of laminations in meter. Thickness of laminations. And V, here it is a volume of magnetic metal. You can have small v here, which is a volume of the magnetic metal in meter cube. So these are called the iron losses, particularly hysteresis loss and the eddy current loss. Hysteresis loss, which is purely a magnetic loss taking place in the iron core, Eddy current loss, which is also an electrical loss, which is taking place in the iron core. And the next one, which is a copper loss or ohmic loss. So these losses particularly occur in the transformer windings, and this is due to the resistance. Ohmic resistance, this is some name which is given for the resistance, ohmic resistance, right? Which is particularly happening in the transformer winding. That's why it is called copper loss. The winding is made from copper, hence it is called the copper loss. If I1 and I2 are the primary and the secondary currents, R1 and R2 are the resistance of primary and secondary winding, then the copper loss occurring in the primary and secondary winding will be given by I1 square R1 and I2 square R2. If you know, this is nothing but the power, I square R, right? We have power P is equal to V into I. The basic formula for power, what we have? V into I. So, and we know Ohm's law, V is equal to I R. So, we can simply put the value of V in this equation. So, when you put this V here, so what we get? I square R. So, this is nothing but the power. So, we can just remember Cu, copper loss, PC or PCU. I square R, right? And this is what including primary and secondary. So I1 square R1 plus I2 square R2. So these losses varied according to load and also known as variable losses. See, current is variable and it is dependent on load. Jasa load वाढवला तसं current वाढणार आहे. So that's why it is called the variable losses. And copper losses varies as the square of the load current. So these are much variable losses. And iron losses, which are called constant losses. These are depends on flux density and the frequency and the voltage. So these are called the constant losses because we are not going to change the frequency, we are not going to change the voltage, flux density. So these are the constant losses. So remember this point: iron losses are the constant losses, and copper losses are the variable losses.